Yuval Ishai. He's over at AWS in New York, and he's from the Technion. And he's done a lot of wonderful work in secure multi-party computation, delegated computation. That's what I guess we'll hear about today.
Yeah, okay, so thanks, Mark, for inviting me, and thanks to the organizers for setting things up. And yeah, so this is actually, I'll talk about a couple of joint works. One with this entire team that was from last CCS conference, it's more applied. And one which is more theory-oriented with the Boconi co-authors, Said Tamer and Alon, which will appear at the upcoming Stock conference. Okay, so let me start with nostalgia. I guess Avi has already seen a different version of this. So I was actually giving a talk in this seminar back in 2002. I was here as a postdoc. Okay, this is how the professors in the Princeton area looked like. How many of them are still here? That's a riddle. Just give me a number.
I guess 3.
3, right? That's true. Yeah, it was hosted by Amit Sahai, who used to be a faculty professor here in the department. These are my fellow postdocs and the junior researchers. How many of them are still here?
It was joined.
Exactly, yeah. It was joined. Yeah, NEC, by the way, was a research lab that didn't exist. And for the junior ones who don't recognize, these are Ronit Rubinfeld, Lance Fortnow, and Joe Killian. And then there were some visiting undergrads, right? So Avi was even back then a source of attraction for elegance and so on. And here too, I guess 2 of those you recognize, right? So Elad was a young graduate student. Sorry, these were graduate students. These were also graduate students, not except for Ishai. So Elad is back here, and Subhash, remember him? Back then. And you know who this guy is? This was the seminar organizer.
Anthony Wood.
Anthony Wood. He was organizing the seminar, and there was Indian lunch. Okay, so it's good to see that there is some rotation in the type of. Anyway, yeah, so it's sort of closing the circle. Great, so I'm going to talk about computing on encrypted data. In a practical setting, think of taking the sensitive data you own. These can be pictures, tax documents, whatever, encrypting them on the cloud, and then being able to do useful stuff with them, research them, or do other things. Okay, so let's, being a theory seminar, let's model it in a precise way. So we have a client and a server. We think of the client being weak, the server being strong. Doesn't have to be this way. The point is that the client just wants to keep a short secret key throughout the process. The client owns sensitive secret data X. We think of X as being very big. Client wants to use its key to encrypt X into X hat and store X hat on the cloud. Okay, so everything that's red is sensitive, is hidden, should be hidden. Everything that's green can be made public. Okay, so it's safe for the client to reveal this encryption of X. This is the offline phase. It's done once. Now the client can forget the data X and keep only the short secret key. In the online phase, we can repeat a virtually unbounded number of times the following process. The client, again, still has the secret key. The client has some online query Q sub I, sends an encryption of this query to the server. The server uses the encrypted X and the encrypted query to return an encrypted answer, which the client can decode using the secret key to get the answer, QI of X. Okay, think of QI as being some useful computation of X, say searching a face in a database of images or searching, doing a web search. So this is the model. And to be non-trivial, in the sense of ruling out a solution where the client just downloads back the encrypted X, we want at least the download communication, ideally all communication to be optimal, but at least the download communication should be much smaller than sending back X. We want the server to learn nothing in the cryptographic sense. So I will make it a bit more precise in a specific context later, but in a cryptographic sense, we want X hat and QI hat to hide both the data and the queries from the server, computational bounded server. And this is very different from practical techniques for searchable symmetric encryption, where you basically, just to give you a gist of what these techniques look like, you apply some secret permutation to your data, and you store this secretly permuted data on the cloud, and now when I want to access a specific location, I access the permuted location. And this is fine if you do it once, but if you do it multiple times, say you want to traverse a data structure, you're leaking the access pattern, which can be very devastating. So we want to achieve the strongest notion of hiding. Another point about the model is that both the client and the server are stateless, except for the client storing the same secret key and the server storing the same encrypted X throughout the online feeds. Okay, and this rules out stateful solutions based on data structures such as oblivious swap. Okay, so this is basically the model. If there is any question about the model, this is a good time to ask. Great.
Actually, just so that I make sure I understand the model correctly. Is FHE going to give you a solution here?
Yes, excellent. FHE is going to give us a solution. We'll talk about that, right? So the baseline solution would be use FHE to encrypt X, and now whenever you want to, this is really the baseline solution that we're competing against. This is. Okay, so Pravesh already gave one solution, and this solution is not super satisfying, both in terms of assumptions. I mean, it seems pretty good. We can get FHE from standard, learning with error style assumptions, but we can hope to do better, and also we can definitely hope to do better in terms of efficiency. Okay, so these are the two questions that guide this talk. And efficiently can take an asymptotic theory-oriented meaning, which is the main focus of this talk, and it can take a more practical meaning, which is the main focus of the different talk. Okay, so in this talk, I'll give a new approach for solving this problem, which indeed gives an alternative to the traditional use of fully homomorphic encryption or partially homomorphic encryption. We will not be as general as fully homomorphic encryption, but we will be able to handle many useful types of queries. Okay, so the functionality is still limited, but still quite expressive. What can we say in terms of feasibility? We can say two things. First of all, unlike FHE, which is a special form, even if you consider FHE in a secret key setting, it still implies public key encryption. Here, again, it's kind of weird, but because the data is encrypted, there is no implication. I mean, this simple idea of secretly permuting the database gives you a hint about why public key encryption is not necessary here. Okay. So we will use assumptions that are not known to imply public key encryption and not for lack of trying. Okay, so we'll use assumptions that if you show that they imply public key encryption, this would be a major breakthrough. Okay, and another feasibility aspect is that our solutions sort of arithmetize, in the sense that if you want to do some arithmetic computations over a finite field, in the encrypted domain, we still do arithmetic computations over the same field. In fact, we're totally agnostic to the field. We make a black box series of the field, which is a feature that no previous solutions achieved. Okay, in particular, if you use homomorphic encryption, you want to do some arithmetic computation over field F, you need to embed it into some bigger ring and then do operations like rounding, which are not black box in the field. Okay, so these are two feasibility features that also have some efficiency consequences. In terms of efficiency, we can really get the best one can hope for, at least in the circuit model of computation. We talk about distinction between circuit and round, but at least if you consider the circuit model of computation, and in some instances of our problem, we can get the computational cost, not only communication, but also computational cost to be as close as we want to an insecure solution. Okay? And this requires a new assumption, which is a variant of a previously studied assumption, which is also kind of theoretical interest related to learning mixtures of simple distributions. So this is kind of the bottom line. And again, homomorphic encryption from an asymptotic perspective, it has at least polylog overhead. Here it's not only constant overhead, but the constant can be arbitrarily close to 1, which is quite unique. I mean, in this domain of secure computation, we don't have any other examples. Okay, so we will talk about two kinds of functionalities. One is private information retrieval, where the database is just, the data is just a big n-bit string. And the query is just pointing to an index in this string. And you want to retrieve this specific bit from X. And the second functionality is what we call encrypted matrix vector product, or EMVP. And here the data is a big matrix over a finite field. Okay, this is the arithmetic part. The parameters, we have m rows. Typically, we think of m as being very, very big for most applications. W is the width of the matrix. We think of it as being moderately big. But again, it can also work with square matrices or anything you like. This is just the typical parameters to have in mind. And the query is just a vector multiplying the matrix. And we can also think of doing some post-processing. For instance, if you want to do PIR with square root communication, fold the database into a square root n by square root n matrix, multiply by an indicator vector of the column you want, and just post-process by throwing out everything except the entry of the column in which the bit you want is there. Okay, so let me motivate in some. I will focus a lot on the private information retrieval question because it's the kind of better studied from a theory perspective. But our solutions essentially solve PIR via the second problem or via some generalization of the second problem. So let me motivate this EMVP problem. Yeah, so the EMVP is a hub for many applications. As I described, you can use it easily to get PIR with square root communication. But you can do more general things. You can do fuzzy searches where similarity is measured by an inner product of two vectors. You can do AI inferences, secure linear algebra. Everything basically uses matrix vector product. So it's a very general purpose tool. Okay, to give you just one example that actually motivated us to some extent, there were these two works that considered practical problems about biometric deduplication. So one is in the context of humanitarian aid distribution. The other is in the context of a project by a company called World ID, backed by Sam Altman, which is aimed to allow humans to prove that they're humans and do it only once. So basically today we know that AI can impersonate humans. And if you want to give every human a unique ID, and only one ID, so that you cannot come again with a fake mustache and get another ID, you need to do something. And what these works proposed is to use biometric data. They looked into different kinds of biometrics, and it turned out that iris code, so physical iris scan gives you can map it to a vector that is such that similarity search with respect to this vector is very hard to fake. So it's much harder to fake your iris scan than to fake your fingerprints. Okay, so how is EMVP related? The idea of these works is that you take every row of the matrix will be the biometric information of a specific user who is already signed up to this service. And now when a new user comes along, you take the iris scan and you compare it to all existing users to make sure it's not the same user trying to register twice. How do you do this comparison? You take a similarity score by a linear product and you basically check that this new user is sufficiently far from all existing users, and then they get their new ID. Otherwise, the user gets declined. But because biometric information is so sensitive, you need to store the biometric information of users in an encrypted form, and you need to protect the query also in an encrypted. Okay, and these are very large databases. Specifically in this work, the width here is 10,000, and the number of rows is many millions. So you need very fast solutions. And these two papers, one of them used the homomorphic encryption, which was very, very slow, didn't scale at all to the scale they wanted. And the other proposed just to use a secret sharing based approach where you have three parties that hold the so-called Shamir secret shares of the data, and you use an honest majority assumption that no two servers collude to get a lightweight solution to this problem. And this is an actual system. You can download the app. They have these three parties, and their security assumption is that no two of these three parties collude. Okay, and each of these parties needs to be super protected because it contains sensitive information. So in terms of trust model, this is much worse than homomorphic encryption because of the non-collusion assumption and because each of these servers needs to be very protected. In a homomorphic encryption solution, you can just reveal the encrypted query to the cloud holds the encrypted database, and everything can be done in an insecure environment. And in a sense, the solutions we propose give the best of both worlds. So we can get the same trust model as homomorphic encryption with the same or even better efficiency than these honest majority solutions. Okay, so this is just some context and some example of what this type of functionality is useful for. And by the way, here this post-processing that you do, for instance, it will return whether there exists, right? So you take the matrix vector product and the output is one bit telling you whether the matrix vector product has a big entry, which indicates there is too much similarity to the existing user.
So are these codes supposed to be code-like, that they're all kind of pairwise far?
So there are standard techniques for embedding the iris code. So this specific work encoded an iris scan as a 0-1 vector of length 10,000. The other way of doing it, if you use bigger domain, you can use shorter vectors. So these are very standard embedding techniques.
And after, let's say you detected a large entry, you also do post-processing when you check if it was exactly equal, or you?
So I'm not sure. This is a toy version of it. It is the paper that is published deals with this specific question. I'm not sure about the surrounding infrastructure and how they do it, but yeah. I mean, you can extend it to top K if you want to do actual, let's say, retrieval of documents, of images. You want top K, you want to get not just one bit, but pointers to the top method and so on. So you can think of other useful post-processing. But the bulk of the heavy lifting is this multiply encrypted matrix by encrypted vector. The post-processing is relatively cheap because it applies to a much smaller piece of information. Okay, so let me give you a very brief overview about PIR, because this is the kind of simpler application. So it was originally studied in an information theoretic multi-server paper in the seminal work of Shor Godel, Kushilevitz, and Sudan, recently recognized by the Stock Test of Time Award. In this setting, it is closely related to locally decodable codes, which people like Pravesh and Avi worked on, possibly others here. But we will consider the single server setting introduced by Kushilevitz and Ostrovsky. And here, forget about the previous setup. Here there is no setup. There is a server who holds an n-bit database in the clear. So it's not encrypted. It's not processed in any way. The client holds an index. The client sends an encrypted index, gets back an encrypted answer, and decrypts the right bit. We want the query to computationally hide the index, the encrypted query to computationally hide the query. Just again, to be self-contained, here we consider the database size also as a security parameter, just to be simple. So concretely what this means is that any polytime server can only get an eligible smaller than inverse poly advantage in distinguishing between any two things. This is a security requirement. And the non-triviality, as before, is that the total communication or download is much less than n bits. Typically, this will be n to the epsilon to an arbitrary small epsilon or even polylog in n. This is typically the type of communication we're aiming for. And I will not mention communication. From here on, whenever I say PIR, the communication is small. It's n to the epsilon for any epsilon. Okay, you can think of it as fully homomorphic encryption for truth tables, in the sense that, you know, the client encrypts an input Q and the server can compute any function of Q homomorphically, with the only caveat that instead of using a circuit representation of the function, it uses a truth table representation. Okay, so its running time is exponential in the length of it, but it's really kind of a degenerate form of homomorphic encryption. Okay, what do we know about PIR in the plain model? It's not hard to show that PIR implies public key encryption. So, you know, relating to Impagliazzo words, it definitely is in cryptomania. On the other hand, all of the concrete, while we cannot show that any PKE implies PIR, almost all of the concrete assumptions from which we know how to build PKE also imply PIR. Okay, so it's we sort of understand the assumptions for PIR. What about efficiency? And here we will look at two metrics. One is cost in the RAM model, and one is cost in the circuit model, where for concreteness, I will later make concrete statements about circuit complexity. For concreteness, when I refer to circuit complexity, I'm talking about counting gates in a Boolean circuit where a gate can compute any function mapping 2 bits to 1 bit. So AND, XOR, you know, this is a gate, this is 1. Okay, so this will be the measure of circuit complexity. Okay, it's not hard to show that for PIR in the plain model, the server has to read the entire database, because if there is some bit of the database which is not read by the server, then this bit will be ruled out from being the bit that the client is after. Okay, so here we need to live with linear computation. But we can only match this up to polylog factors, and in fact, even heuristically, I'm not aware of even heuristics throw in, you know, heuristic obfuscation, whatever, you know, Alex, I don't know, think of crazy use of obfuscation. We have no heuristic candidates for PIR with linear, and this is kind of the low end of FHE. The same holds for FHE, but even for PIR, we have no even heuristic solutions that have linear circuit complexity.
Wow.
Yes.
This linear cost of looking at the whole data can be done once,
Exactly. Very good. You're foreshadowing the next slide. Okay, so really, what Avi was suggesting is this notion of doubly efficient PIR. The motivation is to get sublinear costs in the RAM model. The circuit model still have to be linear.
Why does it do not?
Because syntactically, you encode again.
The three processes, let's say, okay. The security process. There's a three, and when you ask one, you go down some.
Yeah, but this is in the model. I'm talking about like a simplistic model where you take the encoded database and the query and you apply a circuit to them. And because the encoded database has to be at least as big as the original database, the circuit physically has to be wired, has to touch the entire encode. It depends on the model. Okay, you can have circuit models, but again, I'm just saying that in the simplistic simple model where we implement the server as a function of the encoded database in the query, the circuit complexity still has to be linear. But in the cell-probe model or the RAM model, we can of course hope to do better. And again, this is the only change with respect to the previous model, is that we apply a one-time public pre-processing mapping X to a larger X prime as in standard data structure. So it's a data structure that facilitates better PIR. Okay, in terms of assumptions, this still implies standard PIR, so it still lives in cryptomania. We haven't done anything. In terms of computational cost, again, in the rigid circuit model, it's still linear, but in the RAM model, we need to read super constant number of entries for pretty obvious reasons. And we still need to store at least as much as the database, but we can hope for exponential improvements, and indeed such an exponential improvement was achieved in a recent breakthrough by Lin and Weeks. And moreover, they achieved it under a standard cryptographic assumption. If we want to get polylogarithmic cost in the RAM model, so the client reads polylog number of entries of the encoded database, we need to use sub-exponential version of ring learning with errors. I will not say sub-exponential in this talk, but whenever I assume something, sub-exponential. Okay, but the downside, this is an amazing result, truly amazing result, but somehow, it's still, despite a lot of trying, we still don't have any practical version of this result. And I think that perhaps the main culprit is that this involves a multiplicative overhead which is bigger than polylog. Something like 2 to the square root of log n if you try to optimize everything carefully. And this term is also huge in practice. Okay, so even in terms of just the storage costs, we don't have a version of this result that has a constant or even polylog overhead. Okay, so getting linear circuit size or even storage size is open. Even if we're happy with a much relaxed requirement of just slightly sublinear time in the RAM model, we don't have any solutions. And finally, if we try to take the pre-processing PIR model and connect it, view it as an instance of the problem of computing on encrypted data, this is called secret key PIR. And here, there is a client who owns the secret key, and the client encrypts the database using the secret key as in the previous model. Okay, so this is the model of secret key PIR. And now, things become really mysterious. First of all, we can still show, it's not an easy exercise, but we can still show that this still implies one-way function. Again, to get some intuition about why it's challenging, you need to rely on the fact that you make many queries. If you make just one query, then the trivial random permutation approach works. Okay, it still implies a one-way function, and we still have the same lower bounds as before. And then these are results that actually predate, these are joint works with Boyle, Passel, Wouters, and independent work by Canetti, Holmgren, and Richardson. This is a kind of an exotic ad hoc assumption that essentially says that if I take many random low degree curves over some finite fields, say some small, think of a big finite field squared, okay? So you have this plane, street plane, and you take many low degree curves, and now you apply a secret global permutation. This looks random. Pseudo-random. There's enough information. There are more curves than the entropy in the information, so there's enough information statistically. The assumption is that if you apply a global permutation to many random low degree curves, this looks pseudo-random. This has been referred to as permuted puzzles assumptions. There is an upcoming stock paper that uses it for AI watermarking, a similar assumption, so it's kind of nice. There have been a few works that study this assumption, but it's still very mysterious. It looks a bit like the McLeese style cryptosystem assumption. So even though we don't know how to build public encryption out of it, it's really, the assumption is kind of exotic, and it's hard to reason about. So yeah, so this was the state of the art prior to our work. And here we can get the same, essentially the same complexity that the more recent work got from Ring LWE. Okay, but now we have more questions. Is public encryption even necessary? Is one-way function sufficient? How about dropping the doubly efficient requirement? I just want low communication. Which world does this primitive live in? Very mysterious. Okay, I will not have a full answer to this question, just a partial answer. Okay, and here too, there is still the same question of achieving linear circuit size or linear storage. Okay, so let me tell you what we achieved before I give you the technique, which is quite natural and simple. By the way, what time do I need to talk?
I think we have this room until roughly 1:45.
Okay, great.
So yeah, I think about 1 minute.
It's great. Okay, so let me tell you about what we achieved and then about how we achieved it. Okay, so for the PIR problem, we get the feasibility from the standard learning parity with noise assumption. For those who don't know it, it basically says that almost any linear code is very hard to decode in the following sense, that if I give you a noisy version of a random code word, you cannot distinguish it from a random vector. Okay, so basically it says that almost all linear codes, a noisy random code word is pseudo-random. That's what the LPN assumption says. This one uses F2. Yes. Yeah, it's very standard. It has a very strong win-win flavor, which we cannot say about all cryptosums. This would be huge in coding theory if you refute LPN. Okay, so this is considered very, very standard. Under this assumption, yeah, we can get the communication to be into the epsilon for any epsilon, but not without double efficiency. Okay, so it addresses the question of secret key PIR feasibility without double efficiency. But what's interesting is that we know there is Aleknovich, which was one of the figures in the first slide, Misha Aleknovich. He came up with this very nice public encryption scheme based on LPN. But this requires a strong version of LPN where the noise is less than the square root of the block length. Okay, so this makes assumption strong, but we can work with LPN even with a much higher level of noise. And LPN in this regime is not known to imply public encryption. This would be a huge breakthrough if somebody shows that it does imply public encryption. Many people thought about this one. Okay, so Avi and Pravesh have some works that use this and other things like planted assumptions to get public encryption. But from LPN with high noise alone, getting public encryption is a hard problem. Okay, in terms of efficiency, you forget for a moment about assumptions. Okay, we have a construction. The assumption is nice. I will tell you about it later, but we can get the circuit complexity to be 3n. And again, here no cheating. You take x prime, the encoded database, in particular, it is smaller than 3n. It's 1.5n. Okay, this should be the encoded database. And you apply a Boolean circuit jointly to the encoded database and encoded query, and it's a Boolean circuit of size 3n. If we could get 2n, we tried hard, we had several failed attempts, then I conjecture 2n is optimal, and I conjecture it might be possible to prove a lower bound of 2n. Because we could not get the upper bound, we did not get our hands dirty with the lower bound, but it's a nice lower bound question. And alternatively, we can get slightly, this was another open question. Here we don't get the polylog sublinear of LMW, but we get slightly sublinear in the RAM or Selkov model with very good essentially rate 1. Okay, and here we use a new variant of a previous assumption called learning subspace with noise, introduced by Dodi Scala and Lovet. I will tell you about it more later. But in a nutshell, it's essentially assuming hardness of learning mixture of uniform distributions over linear subspaces. Okay, so learning mixtures of simple distributions is a very kind of a popular topic in computational learning theory. This is a problem that was studied and is believed to be hard.
These subspaces are over finite things.
Yes, I will talk about it. Okay. Yeah, and just if you want to get a sense of how we compare to lattice-based protocols, again, now without double efficiency. So yeah, the 3n, with all lattice-based approaches, the 3 becomes polylog. And concretely, if you instantiate for realistic database sizes and levels of security, the 3 is 400 in the best known protocol with purposes. Now, this doesn't necessarily translate to practice, but I believe that with the right architectures, maybe GPUs are sometimes closer to circuits than RAM. I believe that with the right architecture, at least some of this difference will materialize. Okay, for this matrix vector functionality, we get this field agnostic solution, which has many advantages. It helps distribute to the client using secure multi-party computation and so on. Here we do rely on the general version of LPN using the same finite field as the EMVP functionality. This is also by now a standard assumption, in particular the construction, the JLS construction of I/O. This is one of the assumptions it uses. And again, using LPN, we get an optimal solutions up to polylog factors, and it's not completely efficient. And if we use this LSN style assumption, then we get what I claimed, which is nearly optimal computation. Okay, not only communication, also computation. And even realistically, for realistic matrix sizes that come up in applications, like the one that I described, we can get the concrete overhead to be very small. We did cryptanalysis, we benchmarked. It is really fast. Okay, great. And any questions before I tell you? Now I switch to describe how the instructions work. Any questions about results, claims? Okay, so as the title of the talk suggests, the secret behind our approach is to use a pair of secret dual codes. We have one code that is used to encode the data matrix. So every row of this matrix is encoded using a code which is generated by a systematic generating matrix D. Okay, so we write it again without loss of generality. We can write the general generating matrix of the code as identity matrix. With some parity check, entries. And here in the parameters shown in the picture, we have the storage overhead, and this will also be the computational overhead, is roughly 30%. Okay, and we use the standard coding notation where n is the total block length. This is the encoded row is of length k, is of length n, and here k will be the dimension of the dual code, which we use to encode the queries. Okay, so we denote this dual code, it's a generating matrix of the dual code by C. This is an n by k matrix, and k is how much redundancy we add to each row of the matrix. Okay, so smaller k means smaller storage and computation overhead and more aggressive assumption. We need to pay, of course, for making k smaller, but we want k to be a smaller. Any questions? So these two are secret. They're determined by the client secret key, so we can use just the secret key as a seed to a pseudorandom generator, a pseudorandom function that define this code. If we want better efficiency, we can use, this is not needed for the high order bit of how much the server works. This is more needed for optimizing the lower order terms. But you can also use structure codes of the type that are often used in cryptography in the context of noisy linear algebra. So some rings where encoding becomes faster. Okay, how does the protocol work? Again, it's very simple. In the offline phase, the client takes the matrix X. It computes the encrypted matrix X hat by encoding each row of X using the data code, and then adding a random matrix R. Okay, so the R makes sure that the server learns nothing about the database. Of course, we can use a pseudo-random R, which is defined by the secret key. Okay, so we can think of this encoded database as taking the systematic part, right? This is the actual database and adding these particles, 30%. Okay. What do we do in the online phase when we want to query? We have query qi. We might recall that qi is the vector we want to multiply by x. So the client generates an encrypted query in the following way. He takes qi, pads with zeros, and adds a random code word in the query code. Okay, let's see what this gives us. What happens if we multiply the data matrix with this encrypted query? So first, this cancels out, right, because of duality. Okay, so Ci is in the dual code, it's dual to D, so Ci times D cancels out. And now here, we just get X times the systematic part, which is the database, times Qi. The zeros here cancel the particle. Okay, good. So this is what the client uploads. This is the encrypted query that the client uploads. What should the server do syntactically? Just based on what the server sees. So the server has X hat, encrypted matrix. It has an encrypted vector. What can it do? Multiply them, right? So the server will return X hat, encrypted matrix times encrypted vector. Does it look suspicious, by the way, that I changed notation from hat to tilde? That encrypted in the previously encrypted query was qi hat, and now it's tilde? Does it look like it's either notational inconsistency or there is a different reason for that? But let's see that the client can recover what it wants. So if we look at what the server returns and use this identity, we get that what the server returns is the desired answer, plus this masking matrix times the encrypted query. Now the client knows this because it's determined by the client secret key. And the client obviously knows this, so the client can do the unmasking. Okay, is there anything we should be unhappy about this point? I mean, I described the complete solution. The question is whether there's anything. So let's look at the efficiency of this solution. Okay, so this is what the client does, and this is correct.
Okay. You don't care about hiding X right now?
We do hide X because of R. Right? R is yeah.
Something is a bit confusing. I have to multiply R with QI
Yes. Yeah. So okay. First of all, I described our goals in terms of communication. Okay, but yeah, that's a good question. I will address it later. So let's do a breakdown of costs. If we look at storage and communication, they're basically governed by the data code. Okay, the rate of the data code tells us how much we pay in storage and in communication. Download overhead, nothing. Okay, we download the same amount of information as we do in an insecure solution. What about efficiency, online computation? So the server work will be the same as the storage overhead. Again, the overhead will be the same as the rate of the data code. But indeed, as Pravesh pointed out, the client, in terms of computation, is not better off than storing everything and doing it locally. And luckily, there were two wonderful recent works by Braverman and Newman, and independently by Quintana and Zamir, that suggest this notion of a trapdoored matrix, which is a distribution over matrices together. You can generate a matrix that looks pseudo-random together with a trapdoor that allows you to multiply the matrix by any vector with near linear time. Okay, so this helps save the cost of the client. So let me tell you a little bit more about this, because this is also, I think, of independent interest. There are nice algorithmic applications and also a complexity theory. Okay, so the original constructions are based on standard LPN. It's a fairly simple but recursive construction that inherently, even if you make the strongest plausible assumption about LPN, they inherently have at least a polylog overhead. In the sense that, say, if the matrix is an n by n matrix, given the trapdoor, you will need n times polylog n time or circuit size to multiply. In the context of EMVP, it's not a big deal because it's not the bulk of the work is this big matrix, and this polylog overhead applies just to the length of the vector, which is much smaller. So we're not too worried about it from an asymptotic perspective. But still, we wanted to do better, and we give two alternative and more direct EDM constructions that can give constant computational overhead even in the circuit model. The assumptions are more speculative. If you believe our assumptions, I will tell you a little bit about them, and I'm happy to talk about it offline. There is a recent paper of Van Raz that shows that trapdoor matrices can establish natural proof barriers for linear circuits computing linear functions. Linear circuits are circuits that only contain addition and scalar multiplication gates. And the worst complexity for a linear function is quadratic. Of a circuit computing a linear function, there's a lot of work in algebraic complexity in trying to prove lower bounds, and you can define an analogous notion of natural proofs for these linear circuits computing linear functions, and if you believe our assumptions, then you cannot prove superlinear lower bounds for linear functions computed by linear circuits. Okay, what are our assumptions? The high-level idea, and again, I for the interest of time, I defer it offline. The high-level idea is to first consider a weak notion of pseudo-randomness. That just means that if you multiply So you have a family of matrices, distribution over matrices, say n by n matrices. If you pick a matrix from the distribution and multiply it by any fixed vector, you get a random vector. Okay, this is kind of like a one-query pseudo-randomness. It turns out that such families of matrices can be unconditionally built such that the matrix vector multiplication can be done by linear size circuit. Okay, so these are very fast, and these exist unconditionally. And now the question is how to convert this weak notion of pseudo-randomness into a strong notion of pseudo-randomness, and we have two approaches. One is to multiply by a secret sparse matrix, which is good enough for linear size circuit complexity if the matrix is rectangular, not if it's square. If it's square, then we basically conjecture, and we have some interesting things to say about it, that if you multiply three secret matrices from such a family, you get a pseudo-random matrix. Three and not two, there is a reason for that. Anyway, this is yet to be studied. It's kind of, there are a lot of interesting questions around troubled matrices. I think it's a very useful primitive that will find more applications. We've already seen quite a few of them in the last year or so. Any questions about this? Cool. Okay, so now the final part is security. The reason I changed notation is that this is not an encrypted query. It's not secure. Really, it's stupid. It's really stupidly not secure in the sense that let's consider the case where all of the query vectors are zero. Okay, then what does the server observe? It observes just a bunch of vectors in the random vectors in the secret linear code, so it can recover the full seq, the breaking. Okay, so this is just an example. Of course, you can apply this more generally. But as is, this is not secure. And we're pretty used in cryptography to the fact that just clean linear algebra does not give us security. We want to make these queries completely pseudo-random to the server. And now the change that we make is what you expect. So we make these weakly encrypted queries pseudo-random by adding noise. But the type of noise we need to add here is not the same type of noise that we usually add in cryptography. Usually we have an LWAE noise, which means take every entry of your vector and add a little bit of noise, say some Gaussian, or LPN type noise, which says take 100 entries and make them random. Okay, so here neither of these approaches work just because they will hurt correctness. Okay, they will mess up things completely. Instead, we look at two alternative types of noise. One is mixture noise, which means that we mix from the original, the clean query distribution with junk. Okay, so I toss a coin. Either I send you my real query or I send you junk. I can replace junk with any other distribution. So this is mixture noise because I mix the real distribution with some other distribution. And of course, now whenever I use junk, I don't get the answers. So we use repetition or coding to error correct from the good instances that we have. The second type of noise, which turns out to be more useful for us, is planting noise. And this we haven't seen considered before. But here we just take these unsafe encrypted queries and make it safe by revealing a random low-dimensional subspace chosen at random that contains it. Okay, so we plant it in a bigger space. Okay, and with the planting noise, the construction is very simple. It's just the same as before, except that the client sends a representation. Instead of sending this insecure query, it sends a representation of the low-dimensional subspace that contains it. And now the server just multiplies the encrypted data matrix with this matrix representing the subspace, and the client can just span the right answer from what it gets. Okay, so this is believed to be secure if the parameters are chosen right. Okay, and also I didn't specify how we choose the subspaces of planning. So it's really a blueprint for many types of constructions, and we have several useful instantiations of this blueprint.
Okay, the assumption is that when we release this larger subspace, like the assumption is just that this hides the planted vector. Like you don't reduce from
Yeah, I will tell. Let me tell you about this assumption. Okay, so just I want to say that at syntactic level, this doesn't come for free. We have an overhead, right? This doesn't come for free. We have an overhead in the download and in the computation, and we will show you how to mitigate this overhead later. Okay, so this approach works, is secure with the right, we believe it to be secure with the right type of parameters. Just, Alex, the short version is that we have two instantiations, one which is closely related to prior work. So you can call it standard assumption in the same sense that LPN is standard assumption. So we prove security against attacks. Okay, in a sense, we independently reached the same conclusion and then found the old paper that had the same assumption. So it's even better. And we can also say things about relation. Again, the same type of problems have been independently studied by the learning community. So I think we have multiple sources of confidence. And again, we can base everything on LPN with polylog overhead. So this gives us a fallback, and it's still field agnostic and so on. So this tells us that it's not crazy what we want. Okay, so these are, you can think of them as variants of LPN. Okay, so LPN, I think, gives us the strongest source of confidence, that nothing is fundamentally wrong. Okay?
Sure, I can ask you about it later, but it seems worth understanding.
So let me start with the basic version of the assumption that we rediscovered, right? Incidentally, we use the same name as the paper that we found out about it later. So there is a paper, I knew this paper but forgot about it, by Dodi Scalai and Lovet from Stock 09 that introduced for a totally different purpose the following assumption. It's basically, again, as Alex said, it's just the assumption that the mixture noise version is secure. And what does it mean exactly? That you cannot distinguish between the following two games. This is the random game or the null hypothesis. You just get a bunch of random vectors. And here you get the mixture of vectors taken from a low dimension is secret code, right? Of say dimension n/2. So think of rate half code, chose secretly at random. And I sometimes pick vectors from this code, and sometimes I replace them. Most of the time I will replace them with random vectors. Okay, this is the LSN assumption. And again, it has history. It was first applied for feasibility of leakage resilient crypto. But later it turned out that you can use standard LPN to get similar conclusions. The search LSN was studied by this paper by Chen Den. Again, they studied it in the context of of learning mixtures of uniform distributions over linear subspaces. They basically, again, were not aware of the previous crypto paper and reached the same conclusions. So their positive results are the same as the best attacks that were pointed out before. I asked an India about it. He said he'd be very interested if there is any progress on it. Okay. And again, it's a supernatural problem from a learning theory perspective. I mean, learning mixtures of linear distribution, of uniform distributions over linear spaces is very natural. Okay, you can think of previous assumptions for secret key PIR as being structured versions of it. There are some technical differences, but in some sense, these are much more structured versions of the same type of assumption. So when the code dimension is constant, this is equivalent to standard LPN. when we consider the constant rate regime, it implies LPN. The rough intuition is that if you have an LPN oracle, it allows you to find sparse linear dependencies. So it allows you kind of separate the dependencies inside the code from the junk around it. There are non-trivial attacks. In fact, the DKL paper credited Ran Raz. They initially made the wrong conjecture, and Ran Raz pointed out a more clever attack, which basically uses an annihilating polynomial. Yeah, I'm running out of time, so I'll skip to the conclusions, but let me say two things. One is that for this basic version of LSN, the best known attack really means take your sample, apply some constant degree tensor, and try to find the rank deficiency. This is the best known attack.
So in particular, like K has to be at least 1 minus mu times n.
Exactly, yes. So basically, if you have constant rate code, the best security you can hope for is quasi-polynomial. And it turns out that you can get around it in a provable way, in the sense that we provably defeat the algebraic attacks that also Aurora Gaze in this framework. So we can prove resistance to this type of algebraic attacks that gives us sub-exponential security if we use the planting noise. What kind of planting noise do we use for the best efficiency? I haven't told you how to get the LPN-based result, but the LPN-based result is really uses some careful type of mixture noise that implies LSN in certain parameter regime. Okay, I will not get into the details, but we can talk about it offline. Yeah, so the last thing I wanted to show is that this is really the assumption that gives us the best efficiency, the 1 plus epsilon overhead. It's very simple. Every code word is split into a super constant number of blocks. Think of this number of blocks as n to the epsilon. And now you multiply each block by a secret non-zero scalar. That's it. This is your noise. So you can think of it as planting in a linear subspace whose dimension is the number of blocks, but it's a structured linear subspace. And we can prove that this assumption is sub-exponentially secure against the same type of attacks that break the classical LSN, the basic LSN in quasi-polynomial time. Okay, so the paper is out already a year. Cryptoanalysts are free to look at it. Everything is possible, but my guess is that it will survive. Okay, we have one-line conjecture, two-line conjecture. Okay, everybody is welcome to break it. It's cleaner than many of the cryptographic assumptions. It's simpler to define than LWE. Yeah, so it's a new kind of field agnostic assumption, right? More in line with the things done in coding. Okay. Yeah, and when you have this assumption, you basically split the encrypted matrix, and the server has to separately return each block multiplied by the corresponding block of the matrix. And then if you want to avoid the overhead to the download, you can compose it with linearly homomorphic encryption to shrink it. So you can basically get the best of all worlds. This shows that we implemented it and we get a small overhead. We did analysis. And let me conclude. So it's a new approach for computing on encrypted data, applies to limited but useful, much faster than lattice-based approaches. Field agnostic, based on new-ish cryptographic assumption closely related to LSN. Alternatively, we can get everything under standard LPN with polylog server computation overhead, which means that it's not ridiculous. In particular, placing these primitives between minicrypt and cryptomania, it's a real mystery where the truth lies. But this LPN puts it in between. Not in minicrypt for all we know, definitely not in cryptomania. Many open problems, minimal assumptions, are one-way functions enough. Study LSN style assumptions, even search to decision reduction is something we don't know. A lot of analysis generalized to other fields, to reals, right? Professionals thing. Ramesh asked about it, generalizing this to reals. There have been papers studying the learning problem over the reals. The conclusion, the conjectured hardness is roughly the same as in the finite field case as far as I know. Yeah.
There are papers on reverse surface recovery which did not really
So we can look it up. I think that the paper that studies this mixture has the same type of behavior. Better codes, it motivates finding pairs of codes that are both very fast. It's partially motivated the recent ITCS paper by Brehm and Resch to find asymptotically good pairs of codes that are linear time encodable. And extending this to more general functionalities, there is a recent work. I didn't tell you in PIR how we get below square root n. There is some tensoring trick that gets us the complexity to the n to the epsilon. You basically fold the matrix and you encode in every dimension. Okay, and a generalization of this approach can extend from matrix vector to evaluating a dense low degree polynomial on an input, and this was pursued with the motivation. Malvika Joshi was an intern at AWS who drove this project. She's a PhD student at Berkeley. And yeah, they have some very nice applications to lexical search using this generalization. That's it.